Swayam Prabha. Digital India. Educated India.
So, welcome once again to our discussion of econometrics, and yesterday we completed our discussion on dummy variable models. So, that means so far we have gained some knowledge about how to estimate an econometric model. We have learned the estimation technique for two variable linear regression model, then we have also discussed about multiple linear regression model, and then lastly we discussed about dummy variable model estimation. Now, once you know how to estimate the model, before using the coefficients for your policy purpose or for forecasting, what we need to know or what we need to check actually whether the estimated coefficients they exhibit the three desirable properties, right? Three desirable properties, and what are those? If you do you remember what are the three desirable properties that our econometric estimates must exhibit? They are basically unbiasedness, efficiency and consistency property. And if you recall, we discussed about 10 assumptions. If 10 assumptions are satisfied, then only our estimated coefficients, whatever we are estimating using ordinary least square technique, that means using the Wallace technique, they will exhibit efficiency, unbiasedness and consistency property. But in reality, when you get a data set for estimation, there is no guarantee that all those 10 assumptions are satisfied by your data set, because this is a data taken from the real life world, taken from the behavior of particular certain individuals, certain firms or certain countries, whatever, and they are behaving based on their own way. We have no control on that. So, it is quite unlikely that whenever you get a data set, all those 10 assumptions are satisfied. Rather, it is quite likely that one or more than one such assumptions are violated. And if those assumptions are violated, then your estimates will not give you the desirable properties. So, that is the reason from today's discussion onward, what we need to learn is, if those assumptions are relaxed, then what would be the consequences on your estimated coefficients, and how to detect whether any of those assumptions are violated, and what are the remedial measures if such assumptions are violated. So, that means today's discussion would be on relaxing the assumptions of classical regression model. What I am saying? Relaxing the assumptions of the classical regression model. Okay, classical regression model. And to start with, we will relax one assumption, which was, we assume that there should not be any multicollinearity. So, that means today's topic of discussion is multicollinearity. So, first of all, what does it mean? We need to understand what does it mean. What does it mean? When we say multicollinearity, what does it mean? So, let us assume that we are trying to estimate this model yi equals to alpha plus beta 1 x 1 I plus beta 2 x 2 I plus beta k x k I plus ui. You have k number of explanatory variable. Then the term multicollinearity actually means, if you decompose, this is equals to multi plus collinearity, and multi means multiple, and collinearity means linear relationship, linear relation. So, in your econometric model, whatever you have specified, it may so happen that these x 1 x 2 or x 2 x 3 or x 3 x 4, they are actually showing linear dependence, and you have multiple such linear relationship between x 1 and x 2, x 3 x 5 or x 6 x 5 x 7. So, multiple linear relationship indicates the presence of multicollinearity. That is the actual meaning of multicollinearity, but when you estimate a model, even if you get one such linear relationship, and that relationship is called perfect linear relationship. Collinearity, here I will say perfect, I will say perfect. What is the meaning of perfect? I will explain. So, even if you have one such perfect linear relationship, then also we will say that there is a presence of multicollinearity. So, that means literally, even though multicollinearity means multiple perfect linear relationship, when we estimate model, even one such perfect linear relationship also indicates the presence of multicollinearity. That is all. Now, what is the mathematical way by which you will understand? So, basically this is the definition. Multicollinearity means presence of multiple perfect linear relationship among the explanatory variable. This is the meaning. So, this is the meaning, but presence of even a single perfect linear dependence between two explanatory variable also known as multicollinearity. Okay. Now, I will explain how to write the multicollinearity relationship. Let us say that this is our model yi equals to alpha plus beta 1 x 1 I plus beta 2 x2I plus beta 3 x3I plus ui, and we assume that there is perfect linear relationship between x1 and x2, okay, x1 and x2. Then the idea here is lambda 1 x1I plus lambda 2 x2I equals to 0. This is called a perfect linear relationship. Perfect linear relationship. Okay, because in that case you can always represent x1 where lambda 1 and lambda 2 they are two parameters. Okay, they are two parameters. This is the perfect linear dependence. So you can easily express or this is if you can put this as minus, it would be easier. So that means I can say that x1I equals to lambda 2 by lambda 1 into x2I. So if you know the values of lambda 1, lambda 2 and x2I, then you can easily identify what is x1I. This is called perfect linear relationship. But even though the relationship is not perfect but quite high, then also there would be adverse consequences in your estimates. And how will you represent that near perfect relationship? Let us say that this is x1I minus lambda 2 x2I minus some v equals to vi equals to 0, where vi is an error term. So I can say that x1 and x2 they are not perfectly there is perfect linear relationship between x1 and x2, because knowing alpha 1, alpha 2 and x2I, you cannot perfectly predict the value of x1I because of the presence of vi. That is why this is called near perfect relationship. Near perfect relationship. Okay, this is the meaning. Now the question is, why should we bother about multicollinearity? That means if such linear relationship, perfect linear shape exists between two or more than two explanatory variable, what are the consequences of multicollinearity? So let us talk about consequence of multicollinearity. In short, I will write MC, consequence of multicollinearity. Okay. So when I say that x1I equals to lambda 2 by lambda 1 x2I, I can easily substitute the value of x1I in this equation, and then what I will get, substituting the value of x1I into the original equation, what I can say that then yi equals to alpha plus beta 1 into x1I. In place of x1I, I will write lambda 2 by lambda 1 x2I plus beta 2 x2I plus beta 3 x3I plus ui, right. Okay, this would be, so this again I can write alpha plus alpha plus beta 1 into lambda 2 by lambda 1 plus beta 2. Beta 1 I can take this as common plus beta 3 x 3I plus ui. Now, if you estimate this model, the coefficient of x to I would be this. So, from this model, let us say this is equation 1, and after substituting this is equation 2. So, from the estimated equation 2, what you will get? Beta 1 into lambda 2 by lambda 1 plus beta 2. So, that means I will get only the combined value of beta 1 and beta 2, while my objective was to get beta 1 and beta 2 separately. So, that means when there is a presence of perfect linear dependence among two variables, so that means I cannot get beta 1 hat and beta 2 hat separately. Beta 1 hat and beta 2 hat can't be estimated separately. That is the problem. So, I will get a combined value of beta 1 hat and beta 2 hat. Moreover, if you have perfect linear dependence, then what will happen? If you recall yesterday's class while discussing about the dummy variable trap, what we say that your X matrix is basically, X matrix looks like, in this you have 1 1 1 1 1, and then if x 1 and x 2 they are perfectly linearly dependent, then what will happen? Your x 1 I, let us say this is x 1 I, and this column is, let us say, x 1 1, this is, let us say, x 1 1, and this is x 2 1. So, this column and this column, they are now perfectly dependent. So, as a result of which, once again, if that is the case, then what will happen? The determinants is actually become 0. Determinants of this matrix is 0 when there is perfect linear dependence. So, that means beta hat, what you are estimating as x prime x inverse x prime y, that you cannot estimate when there is perfect linear dependence between x 1 and x 2 variable. That is the problem, because you will have your two columns of this X matrix will be perfectly linearly dependent. Collinearity, perfect collinearity exists between these two columns. So, that means from this approach and from this matrix approach, you can easily understand that when there is perfect linear dependence, then your model cannot be estimated. But what will happen? What will happen if you do not have perfect linear dependence, but let us say this is near perfect linear relationship, near perfect linear relationship, I will say. What will happen? What would be the consequences of that? Now, let us say we have near perfect MC What would be the consequence? See, the consequence would be in your estimates, your beta hat, if you take expectation of beta hat is still beta, that means unbiasedness property is still satisfied. So, this implies unbiasedness is satisfied. And then beta hat and beta, the difference between these two is and probability of getting such beta when n tends to infinity equals to 1 minus lambda is also satisfied. So, that means this is called unbiasedness, and what is this called? This is called consistency property. So, this is consistency. Consistency property is also satisfied. Okay. So, even if there is multicollinearity or near perfect multicollinearity, you will still have unbiased estimate, you will still have beta hat which will show the consistency property. But the problem that will happen is the variance of this. What will happen to the variance of beta hat? Variance of beta hat. That means basically we are talking about the property of efficiency. Will we get efficient parameter? Efficient beta hat. Okay. Now, what does efficiency mean? Efficiency means basically if you estimate a model using ordinary least square method, then if all other assumptions are satisfied, then OLS estimates will give you minimum variance in the class of all other unbiased estimates of beta estimated by different estimation technique. But in a given sample, when you have endowed with a particular sample and you estimate the model, what will happen to the variance of beta hat from that particular sample? That we need to understand. And to know about the variance of beta hat in presence of perfect or near perfect multicollinearity, first of all, what is variance of beta hat? If you recall, variance of beta hat was defined as sigma square divided by summation xi square, where xi equals to capital Xi minus x bar. Okay. So, when your model involves only one explanatory variable, that means this is applicable when your model is yi equals to alpha plus beta xi plus ui. So, this is the variance formula when you have only one explanatory variable in the right hand side. Now, when your model involves more than one explanatory variable, alpha plus beta 1 x1 I plus beta 2 x2 I plus beta 3, let us say x3 I plus ui, or let us say I have only 2 for the time being, plus ui, then this particular variance formula changes as now variance of beta 1, in this case variance of beta 1 would be sigma square divided by summation summation x x 1I into square into 1 minus r square 1 minus r square 1 2. You have now two explanatory variable. Okay. So, that means the changes will happen like you will have x 1 I square plus into 1 minus r square 1 2, okay, 1 minus r square 1 2, right. So, similarly now this 1 minus, when you have multiple linear regression model, let us say you have now your model now changes as alpha plus beta 1 x 1 I plus beta 2 x 2 I plus beta 3 x 3 I plus beta k x k I plus u I. And now suppose you want to get the variance of beta, let us say j, okay, beta j, all right. So, what you will do, you have multiple linear relationship, and now when you have multiple variables, how this formula, this particular formula will change? When you have two, you can easily calculate the correlation between 1 and 2 and you can square it off, right. But when you have k number of explanatory variable and you want to get the variance of a particular variable, let us say this is beta j. So, how will you modify this formula? This modification of this formula will happen like summation x j square into 1 minus capital R square j. And what is R square j? R square j is basically, how will you get? By regressing jth explanatory variable on all other explanatory variable and get R square, and that is known as R square j. Is this clear? So, when you have multiple regression model, then this R square j is nothing but the R square from the R square what you get by regressing the jth explanatory variable on all other explanatory variable. And why I am regressing this? Because this regression basically shows if other explanatory variable can explain a significant portion in the variation in xj, that basically shows that all other variables are highly correlated with the jth explanatory variable, quite simple. So, that means they are basically asking you to run this type of regression. So, this is your xj equals to some lambda 1, let us say x 1 plus lambda 2 x 2 plus lambda 3 x 3 plus dot 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 lambda k x k plus some u. So, that means I am regressing the jth explanatory variable on all other explanatory variable and collecting the R square, and that R square is basically this R square. That is how you can change the variance formula. Now, this 1 minus 1 by R square j, 1 by 1 minus R square j, this is given a specific name in the literature which is called variance inflating factor. what I am saying, variance inflating factor. Or in short VIF.